Hello, today my discussion will focus on electrochemistry, specifically on the concepts of the oxidation-reduction reactions or redox reactions. Electrochemistry deals with processes involving oxidation-reduction reactions. During a spontaneous reaction, the energy released is converted to electricity. This electrical energy is then used to cause an unspontaneous reaction. To understand the electrochemical processes, you must know the oxidation number. This number is the charge the atom would have in a molecule or anionic compound if electrons were completely transferred. So here are some guides to help you determine the oxidation number. For free electrons or uncombined state, the oxidation number is 0. Thus, the oxidation number of sodium Na, beryllium Be, potassium K, lead Pb, hydrogen H2, and oxygen 2 and phosphorus P4 is 0. On the other hand, the oxidation number of monoatomic ions is equal to the charge on the ion. Thus, for lithium ion, positive 1, for ferric ion, positive 3, for oxygen ion, negative 2. As a matter of practice, I usually read ions with the element in the oxidation number so that they can eventually be part of my stored memory. Thus, lithium ion is lithium positive, ferric ion Fe3 positive, for oxygen ion O2 negative. Number 3. While the oxidation number of oxygen ion is usually negative 2, in hydrogen peroxide H2O2 and peroxide ion O2 2 negative, the oxidation number is negative 1. The oxidation number of hydrogen is positive 1, except when it's bonded to metals in binary compounds. In these cases, its oxidation number is negative 1. Group 1A metals of positive 1 oxidation number, Group 2A metals of positive 2, and fluorine has always negative 1. And in rule number 6, the sum of oxidation numbers of all atoms in a molecule or ion is equal to the charge on the molecule or ion. And we can use this rule to determine the oxidation number of any atom in an ion species. For example, let us inspect the oxidation number of carbon in bicarbonate HCO3 negative. From rule number 2, the monoatomic oxygen O has negative 2, while rule number 4 states that hydrogen H has an oxidation number of positive 1. According to rule number 6, the overall oxidation number of the bicarbonate ion is negative 1. Think of mathematics when you're doing this. Remember, mathematics and chemistry are BFF. Our equation now is 1 plus C plus 3 times negative 2 equals negative 1. And simplifying, the equation becomes 1 plus C minus 6 equals negative 1. Or we have now, if we transpose the numerical values to the left side of the equation, the resulting equation is C equals negative 1 plus 6 minus 4 and equals to positive 4. Take note that the oxidation state of carbon can vary widely from negative 4 to positive 4, so knowing rule number 6 can be helpful in similar cases. An oxidation-reduction reaction involves a transfer of electrons from the reducing agent to the oxidizing agent. Consider the electrochemical process in the reaction of solid magnesium and oxygen gas to form solid magnesium oxide. That is magnesium Mg plus O2 into MgO. For the oxidation-reduction reaction to happen, a reactant must lose an electron while another reactant will gain the electron. Let us dissect the process to make chemistry easier to understand. According to rule number 5, the magnesium ion has an oxidation number of 2 positive. If you don't remember this rule, consult your periodic table. The properties of the elements can be found in the table. In this reaction, magnesium with a charge of positive will have to lose the electrons. Thus, Mg into Mg2 positive plus 2E negative. What is really happening here? Remember that we have an initial magnesium Mg with 0 oxidation number. If it is going to lose an electron, a negative charge, it leaves behind its paired proton, a positive charge. This means that losing 2 electrons leaves behind 2 protons, and magnesium now becomes a magnesium ion with 2 extra positive charges. Magnesium is the reducing agent because losing an electron means there is a reduction of electron. And when it loses its electron, it becomes the electron donor. But the half reaction that goes with it is called the oxidation half reaction. Seems confusing, and I agree, but the one tip I can give you is store it in your memory. Reducing agent oxidation half reaction. Now, let us go to the oxidation, the oxygen gas. Based on rule number 2, monoatomic oxygen O has an oxidation number of 2 negative. But since we're dealing with a diatomic oxygen O2, it needs to gain 4 electrons. That is 2 times 2 equals 4. And of course, there should be an equal number of electrons on the left side of the equation. So O2 plus 4E negative into 2O2 negative. Again, remembering that the initial oxygen has 0 oxidation number. When it gains an electron which is negatively charged, the oxygen gas has now an extra negatively charged ion. So if it gains 4 electrons, there will also be a total of 4 extra negative charges. 2 times 2 negative equals negative 4. Oxygen gas O2 is ready to accept this donation, hence we call it an electron acceptor. Oxygen gas accepts the electron, therefore an oxidizing agent. But the half reaction that goes with it is called the reduction half reaction. I am going to make it easier for you to remember and avoid confusion. In chemistry, redox is a coin word of reduction oxidation. I'm going to use it to our advantage. If you read it forward, REDOX, remember, reducing agent, oxidation half reaction. If you read it inversely, OXRED, remember, oxidizing agent, reduction half reaction. So, that's it. Okay, back to the future. Remembering the half reactions, Mg into Mg2 positive plus 2 negative and O2 plus 4E negative into 2O2 negative. Oxygen gas needs to gain a total of 4 electrons. As a result, magnesium, which has initially only 2 electrons to lose, will need to lose a total of 4 electrons. So you must multiply the oxidation reaction by 2. The half reaction is now 2Mg into 2Mg2 positive plus 4E negative. With equal numbers of electrons lost and gained, we now have a balanced chemical reaction. Magnesium ion 2Mg2 positive and oxygen ion 2O2 negative will be able to combine into a compound 2MgO. Note, you must copy into the reaction equation the coefficients of the reactants and common coefficients of the combining ion species in the product. Thus, 2Mg plus O2 into 2MgO. This reaction has now reactants magnesium and oxygen with 0 oxidation numbers. The 2 plus and 2 negative oxidation numbers of the product MgO sums up to 0. When balancing redox reactions, it is easier if you are guided by the algorithm. Let us codename the algorithm as WSBAV or WSBAV. Write, separate, balance, add, and verify. First, write the unbalanced equation for the reaction in a unique form. Second, separate the equations for oxidation and reduction half reactions like what I discussed earlier. Third, balance each half reaction for number and type of atoms and charges. You balance all elements but do not include yet hydrogen and oxygen. In acidic medium, add water to balance oxygen and use hydrogen positive ion to balance hydrogen. In basic medium, for both sides of the equation, add a number of OH negative ions that is equal to the number of hydrogen positive ions present. The purpose is to eliminate hydrogen positive by turning it into water, H2O. You form H2O on the side containing both hydrogen positive and OH negative ions, and eliminate the number of water molecules that appear on both sides of the equation. Continue balancing the equation. If the half reactions contain different numbers of electrons, multiply one or both half reactions with an integer that will result in equal number of electrons in both half reactions. Fourth, add half reactions to get the final equation. The electrons on both sides must cancel. Fifth, verify that the equation contains the same type and numbers of atoms and the same charges on both sides of the equation. Check, check, and check. Let us review the example I discussed earlier. You start with the unbalanced reactions Mg plus O2 to MgO. Then the half reactions Mg to Mg2 positive plus 2E negative and O2 plus 4E negative to 2O2 negative. Then balance. This fourth and third step is easier to understand by the engineering students if I tell you that this step is a bit like evaluating simultaneous equations. After multiplying the equations with the integers, you add the variables, in this case, the reactants and or chemical species, taking note of the numerical coefficients and the algebraic signs of the variables. For convenience, especially when you are still a newbie, you can transpose the positive 4E of the reduction reaction to the other side of the equation, and of course it will change sign from positive 4E to negative 4E negative. You may, however, do this with the oxidation reaction instead, but take note that the purpose is to place them on one side of the equation and make it easier to add algebraically. Adding, you have now 2Mg plus O2 on the left side of the equation, while 4E negative becomes 0 or cancels. Then on the right side of the equation, combine the chemical species to form the product, thus Mg with a charge of positive 2 will combine with O which has a charge of negative 2. Then the charges equates to 0. So you have now a stable compound MgO. With regards to the numerical coefficients, which is common to both species, it is simply copied to the product, thus 2MgO. Finally, rewrite your answer to conform with the chemical reaction. Finally, let me tell you this. You don't have to love chemistry, but the journey will be much easier if you open your heart. Think I. It's the eye of the tiger, it's the thrill of the fight, rising up to the challenge of our rivals. Bye guys, enjoy the journey.